Sander Vanderberg talking to us today about deploying NPM packages with the Nix package manager.
Okay, thank you for the introduction. So this presentation will be about something that I've been working on for quite a while, for about 2 years. And this project isn't actually something I really like that much doing. There's actually another reason why I'm doing this, and by basically making the NPM and Nix integration possible, you can do lots of cool things. So, by the way, before I start my presentation, how many of you have heard of the Nix package manager or NixOS? Oh, that's actually quite a few. So, I'm a Nix developer since 2007. I'm using it in my daily work, also on my home computers, and pretty much everything else I could run it on. And yeah, the purpose of the Nix package manager is basically the Nix project is a family of deployment tools. And what they all have in common is that they support declarative deployment. So the idea is you write what you want in the declarative specification, and from one single specification you automate the full deployment process. And the basis of everything is the Nix package manager, but we have other sub-projects as well, like NixOS, which is a Linux distribution built around that concept. We have something called Hydra, that's a continuous integration server built on the same concepts. We have Disnix, that's also a project that I've been doing since 2008. You can use that to model distributed systems consisting of microservices or other web services and deploy them automatically to a network. And there's also NixOps, which you can use to deploy a network of NixOS machines into the cloud, such as Amazon EC2. So, besides automated deployment, the tools in the Nix project also have a number of interesting non-functional properties. So one of them is that all the Nix solutions are generic solutions. So that means it shouldn't really matter what technology you use. If you use the C programming language, C++ programming language, Makefiles, Perl, Python, Ruby, Java, it shouldn't really matter. You can use the Nix package manager for all these technologies. Also, another important property of the Nix package manager is reproducible deployment. So what Nix tries to do is it tries to hide as many impurities that will potentially influence package builds as possible. And that typically means that if the inputs of a certain build are the same, then it doesn't really matter where you perform the build. The build should always yield the same result. Another property of the Nix project is reliable deployment. So in order to support reliable deployment, Nix, for example, ensures that dependencies are always complete, and also offers things like almost atomic upgrades and rollbacks. And another thing that Nix tries to do is it tries to be efficient in the sense that it only carries out the activities that it needs to do and nothing more, trying to make deployment process not unnecessarily long. So if you, for example, take any sub-project in a Nix project like NixOS, if you want to install NixOS on your machine, then this is the typical workflow. So it looks a bit odd compared to conventional Linux distributions. What you do in NixOS is you provide a declarative specification of your machine structure. So for example, this configuration in this slide could represent my laptop's configuration. So you can describe things like, I want to use the grub bootloader, I want to use these file system partitions, I want to use these swap partitions. As a system service, I want to run OpenSSH, I want the X server running the KDE4 desktop. I can also provide all the end user packages that I want, such as the Firefox web browser and the Midnight Commander. And what you then typically do is you run one single command line instruction, NixOS rebuild switch, for example. And what happens is NixOS rebuild switch will deploy the entire machine configuration from scratch. So it will obtain all the necessary dependencies, packages, it will build everything from source code if it's required. It will also generate all configuration files. And the end result is you have a running system with all your system services, your desktop, and everything else that you want. What you can also do is you can change this specification to have different properties, and if you run NixOS rebuild switch again, then it will upgrade the system. And upgrades are always safe, so Nix will never overwrite anything. So you can always, for example, if you break your system, switch back to any previous configuration. And that's also, for example, something you can see in the grub bootloader. You have a question?
Yeah, why did it say almost?
Well, that's because, for example, if we upgrade the system, we use, for example, systemd to manage system services, and they need to be stopped and restarted. And then you still observe a bit of downtime, and that's, yeah, system services are unavailable for a while. So from a static point of view, your system is upgraded atomically, but because you still need to change things at runtime, yeah, there's still observable side effects, and that prevents it from being truly atomic. So this is what the grub bootloader looks like. So if you boot NixOS, by default it boots your latest configuration, but all previous configurations that you haven't garbage collected yet, you can also pick them. So if after an upgrade, for example, you suddenly have no display anymore because your display driver broke, you just pick an older configuration and then you're safe again. So the basis of the Nix project and all its sub-projects is the Nix package manager. So the idea of the Nix package manager is actually its package organization, which looks a bit scary if you look at this slide. And the scary part is actually the file names. So the Nix package manager stores everything in a so-called Nix store in isolation. And as you can see, the first component of each path is a hash code, and we derive that hash code from all involved build time dependencies to build the package. So, for example, the source code, the versions of the compilers, linkers, the build scripts, all these properties are reflected in the hash. And if I would, for example, upgrade GCC to a newer version and I would compile Firefox again, then it will yield a different hash code. And because every package has a hash prefix and a unique name, we can easily store multiple variants of many packages safely next to each other without any interference. Another property of the Nix package manager is the Nix package manager, like NixOS, is also declarative. So it uses so-called Nix expressions to build packages from source code and its dependencies. And in this slide, this Nix expression is used to compile OpenSSH from source code and its dependencies. So a Nix expression, for example, the expression shown in this slide is basically a function definition in a purely functional programming language. And the first line is basically the function arguments of that function, and they correspond to the build time dependencies that you need to build the package. So the first two arguments, the stdenv, that's a standard Unix environment providing common Unix utilities like cat and ls and make. Fetch URL is something that can be used to download files from external locations. And OpenSSL and zlib are required library dependencies of OpenSSH. And what we do in the body is we call the make derivation function. That's basically the Nix way of saying I want to build something from source code. We provide some metadata as parameters like the name and version. And we download the OpenSSH tarball from the OpenSSH server. And what we do in the body is we provide a number of build instructions to build OpenSSH from source code. So OpenSSH uses an autotools like build procedure. So that basically means untar the tarball and run configure make and make install. So there's one practical issue with this expression. So this expression basically describes how to build a package from source code and its dependencies. But we also, for example, need to know which version of zlib do we want to use and which version of OpenSSL. And that's actually done in a second expression. So the first expression here is basically a function definition, but you need to invoke a function with function arguments. So what I do in this expression here, for example, is I import my expression in the previous slide, and as function parameters, I provide the build time dependencies that I want to use at that moment. So that means a specific version of OpenSSL and a specific version of zlib. And also all the other packages, OpenSSL, zlib, Perl, and even glibc are composed in a similar way. And if you would run, for example, in the command lines instruction, this this instruction here, what it will do is it will build all the build time dependencies first and then the package itself, and the end result will be a Nix store path corresponding to our OpenSSH build. So using hash codes to isolate packages, that's quite nice, but the inconvenience is if you're an end user and you want to start, for example, Firefox installed by Nix, there's no way that you can remember hash code. So you need some kind of mechanism built around it to make packages more accessible. So for this, Nix introduces the concept of user environments. So the idea is, if you as an end user install packages, what happens is it will compose a user environment, as you can see in the top, and that's basically a symboling tree, basically synthesizing the contents of all the packages into one huge symboling tree, so that becomes accessible from one single location. And it also uses a number of indirections. So each time you install software, there's a generation symlink created that refers to our user environment. And there's also a current symlink referring to our current set of installed packages. And by adding the location to that symlink in the user's path environment variable, if you would, for example, type Firefox on the command line, because it indirectly resolves to the user environment, you can start Firefox. So with a number of indirections, you can circumvent users from remembering hash codes. What you can also do at some point is you may want to update OpenSSH to a newer version, for example. And what would happen is if you run this command line instruction, it will install a new OpenSSH version next to the existing packages, so nothing will be overwritten. And then it generates a new user environment with a new version of SSH inside it. And then it creates a new version symlink, 43, and finally it flips the current symlink to the latest generation. And flipping a symlink is actually an atomic operation on Unix. And because flipping symlinks is atomic, also package upgrades with Nix are atomic. Then there's another thing, you might also want to get rid of obsolete packages. I can imagine that you want to get rid of this old OpenSSH version that's highly insecure. So in Nix you never directly remove packages. What you do instead is you simply remove it from your user environment. And the Nix package manager sees which paths are still reachable from a generation symlink. And by removing the old symlinks, for example by executing this command line instruction that removes the symlink 42, Nix sees this path is no longer reachable, and if you're in the garbage collector, then it safely removes all the packages that are no longer in use. And also, besides user generation symlinks, open files and running processes are also considered garbage collector routes. So that means if your program happens to be running, Nix will not remove it. So you can basically always run Nix collect garbage at any point in time without being afraid that something that you might use is accidentally deleted. So I've shown you this expression for OpenSSH. Now some people tell me that Nix is actually a build tool, but I think that is basically a mistake. Nix is actually not building anything. What it actually does is it complements existing build tools with a pure environment. But in that environment you can basically run whatever you want. You can run make, but you can also run other build tools like CMake, Sconce, Ent, and you can build any kind of software in it. So to make builds pure, Nix basically takes a number of precautions in the build environment to take as many side effects away that will potentially influence the build reproducibility. So for example, what Nix does is it clears almost all environment variables, or it sets them to dummy values. But it also does with search environment variables like path or Python path. It configures them in such a way that they only contain the Nix store paths of the packages implementing them. So you can't use global dependencies. You can only use the Nix packages that you have specified. And if you forget to specify, for example, dependency, then the build might fail. But that's actually a good thing, because if we would silently allow a build to succeed because of a global dependency, that means it might work on my machine, but it might not work on another machine. It also does some other tricks. So for example, it only allows packages to write in designated output folders. So if you build a package on your machine, it isn't allowed to pollute your file system. It can only write in one designated output folder, and that's it. And it also does things like resetting timestamp to 1 and it can optionally use CRUD environments to even reduce the amount of side effects even further, and it also restricts network access while doing a build, and that's also a good thing, because if you would, for example, download a file from a remote server, you don't really know for sure what you get, unless you, for example, provide an output hash allowing you to validate the end result. So in Nix, network access is allowed, except if you provide a build with an output hash against which we can validate. So what I basically explained is that Nix has all kinds of nice features, right? So reproducibility, reliability, and you can also use it for many kinds of software. But what about Node.js? Is here anyone using Node.js, by the way? So quite a few. So it would be nice that we can also have best of both worlds, right? So we use Node.js, but we also at the same time want to profit from Nix's nice deployment properties. But there's one problem. If you use Node.js, you basically can't get around NPM. Is there anyone using Node.js without NPM? Which package manager are you using?
Are the geeks important?
Oh, okay. That's interesting. Yeah.
Is that Yarn?
Yarn, yes, yeah. And IED, that's another project I'm aware of. But yeah, most people are using NPM, so there's basically no way around it. But the problem with NPM isn't a build tool, it's also a dependency manager. And that actually conflicts with Nix's dependency management features. And also Nix gains all its potential benefits from the way it organizes dependency management. And if you would bypass that, yeah, then there's no point in using Nix, right? So this is basically how you would normally, I guess most of you probably already know. For example, if you have a development project, what you typically do is you provide a package.json file that might look like this. You provide some metadata and, for example, you provide the dependencies that you want. And what you then do is you run npm install on the command line, and what npm does is it fetches all the dependencies and puts them into the node folders of the same project. Now, how can we deal with this conflict? The solution is actually quite simple from a theoretical perspective at least, is you just substitute the conflicting dependency manager by doing the dependency management yourself in the Nix environment. And if you somehow fetch the dependencies yourself first, then Node npm doesn't have to install them anymore, right? That sounds very simple. So basically you could do something like this, right? So this is the npm install instruction that I run in the Nix expression. And before that, I somehow obtain the Node dependencies I want, and I put them in the Node modules folder. And what I can even do is, if you take a closer look at this expression here and the package.json, you see that they capture quite similar properties. So I could even automatically generate the Nix expression. So everything appears to be quite straightforward, right? But is it really that straightforward? So I have to tell you, it's actually much more complicated than just that. And yeah, there are actually many reasons for that. And the first reason is, if you would look at for example, the package.json documentation, then you'll see that NPM has many kinds of dependencies. For example, it has a concept of dependencies corresponding to runtime dependencies, but also it has the notion of development dependencies. In Nix, there is no notion between runtime dependencies and build time dependencies, in the sense that you just provide the dependencies to a builder environment, and the builder should figure out what to do with it. NPM also has peer dependencies. That's basically used as a conflict resolution mechanism, but the NPM authors don't seem to know themselves even what it's supposed to mean, because in older versions peer dependencies were also automatically installed, but later they changed this behavior to purely a check. So you also have to cope with that difference in generating an expression, for example. And also it has bundle dependencies, so bundle dependencies are basically node modules already in the package that you don't have to download again. And also it supports optional dependencies, in the sense that optional dependencies are allowed to fail. And if they fail, then the package installation still succeeds. And that's also somewhat incompatible with the Nix deployment model, especially if these failures are non-deterministic, for example, because of a network failure or something. But if we want to create a generator, what we basically only have to do is we only have to look at the dependencies and development dependencies if they have been requested, and we have to subtract the optional dependencies. And peer dependencies, for example, we don't have to do anything with them because they're merely a check. Then there's another thing. Version numbers in NPM are basically semantically versioned. So that means they consist of 3 version components having a specific meaning. And these version numbers are typically used to refer to packages in the NPM registry. What you can use is you can use precise version numbers. They refer to one specific version in the NPM registry, but you can also use version ranges. So you can specify things like I want the version of this package to be 1.0.1 or higher or something like that. You can also use tags, and tags indirectly resolve to version numbers. But besides NPM packages that come from the NPM registry, you can also use your own external location. So you can also refer to dependencies in your own home directory. You can refer to Git URLs. You can refer to repositories on GitHub and Bitbucket and so on. Now, if you want to make a translation, so in Nix we use hash codes to identify packages, and in NPM they use a name and a version number. So how can we make a translation between these 2 means of specifying versions? And there's only one solution from my perspective. So, for example, converting a specific version is easy because you know what you get from the NPM registry. But if you have a version range, for example, any version higher than 1.0, that's incompatible with Nix, because if, for example, you would relate a hash code to a version range, that means if I would download the package today, I might get version 1.0, and tomorrow I get version 1.1. And I still get the same hash code. So I lose the ability to reproduce. So the only solution to cope with this is you snapshot basically the version that that you want to use. So you basically look at where does that version range resolve to today, and I use that version, and I generate an output hash for that, and that's what I use for my packages. Then there's another challenge, and I have to admit that this is actually quite difficult to explain because the first time I studied this, I think it baffled me at least 10 times. And if you don't understand what I'm explaining in the next 2 slides, I forgive you because it's still baffling me in some sense still. And also feel free to ask questions about it. So in Node.js, you have the CommonJS module loader system. So if you would, for example, refer to a module that's provided as a package, for example, the / package, that's one of my own modules, what it basically uses some kind of lookup strategy. So it will first consult the node modules folder of the project, but if the package isn't in there, it will consult the parent's node modules folder and will recursively look upwards until the dependency has been found. And this has all kinds of implications. So this is also, for example, how private and shared dependencies are implemented in NPM. So a private dependency is basically just a dependency residing in a package node modules subfolder. And any package that can be reached through a parent node modules folder is a shared dependency. Now having shared dependencies and private dependencies is nice, but there are some things you may probably not know about NPM. So if, for example, you have a package that declares a version range, like I want a package that's 1.0.0 or higher, and there's a shared dependency that's older than the newest version, it will use that shared dependency instead of downloading the latest dependency from the NPM registry. So in certain scenarios, it might happen that you don't use the latest version, while you might expect that you have. And I think this is really, really bad, because you might reintroduce security flaws, for example, that of which you have, you would probably have expected them to be resolved. And the same thing is also cycles are allowed, and there are actually quite a few node packages depending on packages with cyclic dependencies. But NPM, I don't think it's the author's intention to permit cyclic dependencies, but because they use this strategy in which they don't install shared dependencies again, they break the cycle. But for our generator, we have to simulate that kind of odd behavior, because in Nix you can't, cyclic dependencies aren't supported. So if you would, for example, use any version of NPM lower than 3.0, what happens is if you run NPM install, then all packages are installed privately by default, unless there is a shared dependency already satisfying any of the version specifiers. So what you can see here, for example, is an example web application that depends on Express and EJS. And these are accepts and array flatten and content disposition are dependencies of Express, but they're installed privately for the Express package. What happens in the newer NPM, so in 3.0 and higher, everything is shared by default. So what would happen is it will move all the library dependencies as high in the node modules hierarchy as it possibly can until a conflict has been encountered. So what you see, for example, here is that the dependencies of Express, so accepts, array, flatten, and content disposition, are in the same folder as Express itself. So that's also quite strange. So the first time I saw this, I sort of had a headache, like, oh man, how am I going to deal with this? I don't know what to do anymore. Also the NPM developers realized that they made a mistake, because what, for example, happens if you have a project and you run npm install, and at some point you change the packages and you run npm install again, then the resulting node modules tree is different than a fresh npm installation. So the order in which you install packages suddenly matters. So npm install isn't deterministic anymore by introducing flat module installations. So in my generator, because of all these properties, for example, flattening the node module's dependency tree is an imperative operation. That means after I've built packages, I need to modify the dependency tree in such a way that it becomes flat again. But Nix packages can never be changed after they have been built. So I have to find for another solution in the generator to deal with that. And the only option I see is I need to compose the entire dependency tree ahead of time. So instead of translating an npm package to a Nix package, I basically translate an npm package and all its dependencies to one single package. And that's basically the only option I can think of. And then something else. So in my presentation, I had this theory that if I would provide the dependencies of npm myself and I run npm install, then I don't have to download anything anymore. But it is also not entirely true. If you use, for example, Git URLs in your package.json, then for each npm install run, npm will always try to remotely connect to the repository to see to what version it resolves. So I need to bypass that, and what I do currently is I bypass the version number by a star, but that's not really a nice solution because sometimes npm gets confused by it. But better would probably be to fake the Git process to always give a deterministic result. But that's still a work in progress I'm thinking about. So the solution, so if I would take all my lessons into account that I've described previously and I create a tool out of it, which I actually did, then I can use Nix to deploy node packages, right? So I have the solution. Well, sort of the solution. I mean, there are still some flaws in it, but it works. We can actually get quite far with it. So how can you use Node to Nix? For example, you can use it on project level, so that's particularly useful if you're doing development. I can actually show you how it works. So, for example, this is the Node to Nix generator tool that I've created. It's a Node project itself. What you would normally do in development mode is you run npm install to get the dependencies. What I can also do instead is I run Node to Nix to generate Nix expressions instead. Oh, maybe I should, it's better? Yeah. So I already generated the expressions in order to save time, but this is what you get. And what I can then do, for example, is I can run the Nix package manager to build my project. And this should be relatively fast. Let's see how much time this takes. Okay, I already pre-built the package, but this is the resulting package. As you can see, it also has a Nix store path with a hash prefix. And I can simply run my tool like this. And it should, it should work just fine. What I can also do is, what I just did is I created a package that you would normally use as an end user. But what you can also do is you can start an interactive shell session, like this. And that's really useful while actually coding. So if you're coding, you also need all NPM dependencies to be present in order to run your tool. In this shell, basically the nodepath environment variable has. Oh yeah, yes. So yeah, as you can see, the nodepath path environment variable has been configured to contain all the node dependencies that I need. And also in this shell, I can, for example, run my tool like this. And because the nodepath environment variable has been set to the dependencies obtained by the Nix package manager, it works. Another use case is, this is particularly useful for end user packages. So if, for example, you want to run Bower on the command line or the grunt CLI, you can also specify in an array the packages you want, and you can use any version specifier that NPM supports. And from this JSON file, you can also create a Nix expression allowing you to deploy any package from the package set, like node to Nix. So normally you would use npm install -g, and this is actually a Nix alternative for npm install -g. And there's also a third use case. So there are also some tools using npm as a plugin manager. For example, Grunt is a build tool, and it uses npm to obtain the Grunt plugins. And what you typically do is you define them as development dependencies. What you then do is you run npm install, and then you run grunt build after you do npm install. And this workflow is also supported by Node to Nix. So what you can do is you can provide the global packages that you want in a supplemental JSON configuration. And if you generate an expression like this, so you provide the package JSON file, but also the supplemental JSON configuration, then you can fully automate, for example, a grunt workflow. So what I, for example, specify in the expression here is I overwrite the earlier expression, and I state here that run after npm install run grunt. And then I can build grunt projects in a Nix environment. And you can also use this for other builders, so for gulp and ESLint, this also should work fine. So yeah, that basically concludes my presentation. So what I've been trying to explain in this presentation is the difference between Nix and NPM's deployments concepts. I've also shown you a Node to Nix, which you can use to generate Nix expressions, so that you can use the Nix package manager to deploy NPM packages. And why is this useful? So besides having the Nix package manager to deploy Node packages, you can also, for example, include Node packages in your NixOS configuration and deploy it as part of an entire system. And you can even deploy entire networks of machines with Node processors inside them. And that's actually why this Node to Nix generator is such a great thing. It's quite a pain to develop it, but the potential applications that you can build on top of that is awesome, I think. So, and then there are some lessons I learned from this experience. So if you, for whatever reason, need to develop a language-specific package manager yourself, I would advise, first of all, think about how to name packages. So I would say naming a package by a name and a version only, that typically doesn't suffice. So in Nix, we use hash codes for that reason. But also if you take a look at Microsoft, for example, they use for the .NET Global Assembly a concept called strong names, which includes cryptographic keys. Also, organization is important, so isolate your dependencies well. Don't put them in some kind of global namespace. And also cyclic dependencies, disallow them. I see this quite a lot, but packages are supposed to be units of reuse. And if two packages are mutually dependent on each other, then yeah, it's no longer reuse anymore. They should ideally belong together. So if you want to know more, this is not Node to NIX is not the only generation attempt. There's also NPM to NIX, which is actually older than Node to NIX. It's actually much faster because it actually constructs packages for each NPM dependency, but it's less compatible. And there's also a Haskell implementation called NIX from NPM that implements the same concepts, but they also support partial regeneration to make things faster. And then there are also some NPM alternatives. So there's Yarn, for example. The main difference between NPM and Yarn is that Yarn, for example, supports a lot of parallelization to improve the speed of the deployments. And it also supports version locking. So whenever you install a version from a version range, Yarn will create a Yarn log file pinpointing your installation to that version, so that you can reproduce an installation elsewhere. And there's also IED, and IED, I think that's a really nice effort because the author, first of all, says I basically use NIX as my inspiration source for developing this package manager. And also he supports things like a content addressable store, atomicity, and maximal sharing of dependencies. So if you want to know more, so here are some references, the NixOS website, a link to the Nix package manager, and of course the Node to Nix generator itself, so that you can start using the Nix package manager for deploying your NPM packages. So that's it. Any questions?
Yeah, you explained that A, the previous inputs are used to generate the hash,
Yeah.
and B, that the build is to be deterministic.
Yeah.
So what happens if I have, let's say, a C program that uses the timestamps at which it is built to display it at runtime? I build it twice, it will have the same hash, but the build output.
Yeah, that's a very good question. So in an earlier slide, I've shown you the some of the precautions that Nix takes. I think they're here. But this is not sufficient. I mean, there are still ways to cheat and get impurities sneaked in. And timestamps, the ones you refer to, like if you would, for example, use a C call to obtain the time, yeah, then you have an impure build. So that's not something Nix would guard you against. So Nix has lots of means to guard you against certain things, but by no means it's enough. So, and timestamps is actually still the biggest source of impurities, but we're working on that.
So, did you guys have similar hurdles when building Cabal to Nix? And is there a pip to Nix as well?
There is PyPy to Nix, but I have to admit that I haven't used it myself that much. And there's also Cabal to Nix. And Cabal to Nix, I must admit, it's been over 10 years ago that I did Haskell development, so I'm probably not the best person to ask, but we have a very mature generation tool already, supporting actually quite a few packages. So there's actually a developer spending a significant time of a significant portion of his spare time in making that generator. Other questions?
So, just at one point, so you said that the hash loops, the hash of the build. And there's one point, I thought you said that the hash would be the same if there was a version of one of the input hashes nowadays. So, can you just clarify that?
I couldn't hear you, but it was about hashes, right? So,
Hashes,
yeah.
What is actually included in the hash? And is it affected by downloads?
Oh, you mean which properties are? The question is which properties are included in the hash?
Yeah.
Yeah. So that's basically. So hashes are actually computed recursively in Nix. If you want to know more about it, but for example, if you take this expression here, as you can see on top, that's a function declaration. The function header is the first line, and. What you basically do in the body is you invoke the make derivation function. All properties to the make derivation function, all function parameters are, except for the meta property, but that's not used in this slide, is basically used to compute the hash.
Is that included the contents of the tower file?
Yes. Well, actually the output hash of the tar file is used. And the same thing, for example, with the dependencies. So OpenSSL and zlib are basically Nix store paths having own unique hash code as well. So hash codes are computed recursively. So that also means, for example, if you use another zlib function, yeah, you have a zlib with a different NIC store path, and as a result, the hash of the corresponding build will also be different. Yeah.
Do you know if there were experiments to run the NIX package manager on other distributions than NixOS?
That's also an interesting question, yes. So the NIX package is the basis of NixOS, but it can also be used as an independent package manager in other systems. And besides Linux, also, yeah, you can use conventional Linux distributions, of course, but also Mac OS X is quite well supported. Some people want to make it an alternative to Homebrew. And there's also some limited success with Nix on FreeBSD and Cygwin and OpenBSD and several other Unix clones.
About the Darwin support?
Yeah. Yeah.
Maybe it's part of the NixOS rebuild stuff?
Could you repeat? So it's about Darwin?
Yeah, so on OS X,
Yeah.
I have made partial support for rebuild by
Yeah. I still don't know what the question is. Maybe you, because you're in the back. Oh, okay, sorry. Okay, never mind. But it's great that, yeah, contributing to Nix, that's, yeah, it's awesome. I mean, I appreciate it very much. Other questions? Or? Oh, yeah.
So the Nix command line tools, like NixM from
Yeah.
they're sometimes a bit difficult to use, I guess mostly for the storage reasons.
Yeah.
And there was some GitHub issue or pull request about like re-implementing
Yeah.
that whole command line system, but I think there's not so much progress in this project.
Yeah, so yeah, there's indeed, NixEnt, for example, was historically inspired by RPM, and also the command line options that it implements are similar to it. Yeah, there's indeed a new effort. I think it's already in progress for a year or something like that. But I believe there are many more big things ongoing in the Nix code base. For example, also reorganizing substitutes and stuff like that. And I think it will still take a while before that completes. But you have to ask the Nix maintainer. He's doing most of the development work on it. So, yeah.
Are you trying to distinguish between already compiled and minified JavaScript? So do you try to build JavaScript packages completely from source, or do you download the minified JavaScript files?
You mean as an NPM dependency or in general? Well, we try to mimic whatever NPM does in certain scenarios. So if that happens to be a minified version of JavaScript, yeah, then that's also what you get. There's no specific objective besides mimicking what NPM does, because I also would like to change many things to NPM if it were me to decide, but yeah, I'm afraid I can't do that. So yeah. Other questions? Yeah.
You have certain packages, I think, like fibers.
Yeah.
When you install them, the binary will be compiled.
Yeah.
How do you handle that?
You mean how to handle software that isn't available in source form, or?
Yes. So.
Yeah.
Yeah.
Yeah, that's also a very good question. So yeah, in principle, Nix is a source-based package manager. It supports binary deployment, for example, by its reproducibility properties and the hash codes. For example, if you install NixOS and you compile a package yields a hash code, and it also, for example, sees, hey, there's a build server remotely with a package with an identical hash code, so I can download that instead. But there's also indeed software that doesn't exist in source form, and in order to make them work, that's quite tough actually in Nix. There's actually a tool called PatchElf that you need to use for that purpose. Because, for example, binaries compiled, ELF executables compiled in the Nix environment have the paths to the libraries they need hardwired into the RPath header. And for pre-built binaries, there is no RPath header with the locations to the libraries. So if you would run a pre-built executable on the Nix OS, then it won't work. But there's a tool called patch ELF that you can also run in Nix expression to provide the missing build paths. And then the patch executable will run without problems on Nix OS. Other questions? I guess that's it.